So thanks everybody for joining and otherwise watching online later. Today, right before the Thanksgiving break, I know it's kind of the crush for a lot of people, a lot of students and classes and even professors to get the last couple of projects in before the Thanksgiving break. So thanks for those that could join here and are about to join maybe, because I forgot to send out the reminder this morning, which is also I don't have any classes or anything, but I guess I'm feeling it as well on the crunch. So, but without further ado, today we have Shane Coyle, who will present on substorms and eclipses. So it's an interesting combination of two phenomenon. One which is more common, but sometimes more debated, and the other one's very rare. And yeah, I think you kind of got it there on that front slide of what I was getting to. So yeah, so without further ado, Shane, yeah, go ahead and take it away.
Yeah, thanks, Kevin. Yeah, so definitely didn't want to bury the lead here. I've kind of answered the question here, but I'll go through the process. So eclipses and substorms, right? We're looking at the correlation, if there is one that exists between them. And yeah, I've kind of lined it up. Substorms happen pretty often. Typically a couple a day. They happen often during eclipses as well. Eclipses are, obviously a lot more infrequent, happening, maybe 2 to 5 times a year. And so this kind of arose from a case study where we had looked at an eclipse in Antarctica, and there was a substorm coincident with that eclipse. And, it kind of led to the question, well, how often does that happen, right? Because the previous Antarctic eclipse also had a substorm occurring, relatively close to it. And so we wanted to see if that's a feature or a bug, right? And yeah, like I said, I think based on the evidence I'm about to present that the answer is yes. Substorms do happen more often during eclipses. And at the very end, I'll maybe briefly touch on some reasons why that might be. But let's get into it. First, some definitions here. So we're talking about geomagnetic phenomenon, and there's two primary phenomenon that occur that we're concerned about. The first being geomagnetic storms, which are much larger events. They last for days. There's a couple that happen every month, to a couple that happen every year, depending on where you are in the solar cycle. And they are enhancements of the ring current, and they are observed all over the Earth, right? Whereas geomagnetic substorms, they're substorms, right? So they're not as intense, or rather, they're not as pronounced, right? They don't typically have a global signature. They're much more localized. They are much more frequent. So they happen, like I said, a couple of times per day. And they are most well observed at higher latitudes. And this is because the magnetosphere configuration that causes them, the actual region of the magnetosphere that's supplying the currents, is in the tailward region, just kind of outside that dipolar region where things start flattening out and the magnetosphere becomes more tail-like. And so that happens farther away from Earth, which corresponds to the higher latitudes. That said, substorms can be enhanced during storms. And so I have pulled out here, this is the DST index, and this is kind of a proxy for how strong the ring current is. And we can see, on this day, you've got some substorms that are occurring, throughout the day, right? Whereas the next day, you've got a storm occurring. You see this, relatively significant dip in DST, and you can see there's a lot more activity in this index. And so this, again, to give kind of some background information, this is what's called the auroral electrojet index. And this corresponds to the strength of currents in the high latitude region, high latitude ionosphere. And so when this is particularly large, you have a lot of activity in that region. You have currents coming in from the magnetosphere into the ionosphere, and so that's corresponds with a substorm. And a picture of aurora, because you can't talk about substorms without talking about aurora. This is the currents, the particle populations slamming into the ionosphere and breaking and causing this terrific light show. And that, like I said, is part of what's associated with geomagnetic substorms. So moving on to eclipses, right? How does that impact what we're talking about here? Well, we know kind of what the eclipse does on Earth as far as things like photoionization, right? You're blocking the sun's rays from reaching Earth, and so that blocks those photoionizing photons, right, from reaching the atmosphere. And that corresponds with a decrease in the ionospheric conductivity, right? Because you have less production term in your chemistry equation there describing, the production of ions. And so if you lose production and your recombination stays the same, then you're going to have a total loss of electrons and free ions and those kinds of things. So the conductivity is going to go down. And also, if you've ever been outside during an eclipse under the path of the shadow, you felt on the surface of the Earth a pretty stark temperature difference, right? And so in the atmosphere, that's going to be noticeable as well. And so you're going to have thermal gradients that follow the track of the shadow throughout the atmosphere. And so we know about these things. They're well established, well studied, but we have perhaps a less cohesive understanding of how those kinds of activities and other impacts may play out in terms of ionospheric currents, and how the layers in the ionosphere and in the thermosphere move around because of thermal gradients or whatever. And I'm going to talk about specifically this last bullet here today, the magnetospheric impacts. And so, my group studies magnetosphere and ionosphere coupling. And typically that conversation goes, something happens in the magnetosphere, and then we see that mapped into the ionosphere. But it's, it's of some debate whether or not something that happens in the ionosphere can then feed back into the magnetosphere. It's not very common, right? And if it is common, it's not very influential, we'll say. So eclipses kind of provide a unique opportunity to study this, because all things aside, they don't really impact all the other typical magnetospheric drivers of currents and storms and substorms and so on. They're really directly attached to the ionosphere. So if they change the ionosphere dramatically and that changes something in the magnetosphere, then we can use that to infer what that kind of feedback relationship would be. And so, to kind of get the electrical engineering aspect of this, you might think of our current systems in the solar wind magnetosphere ionosphere coupled system as this figure from Bostrom 1974. And this is the ionosphere. It's typically modeled as just a resistive load on the magnetosphere. Call this your voltage source, right? There's some potential across the tail, and then that feeds currents that go into the ionosphere and back. If you change this R value, you're going to change the currents in this local loop here, and that's what happens during an eclipse. Is you change this R value in one hemisphere at least. And so there's some intuition here for how an eclipse should impact the currents that flow in the magnetosphere and ionosphere system. And so kind of the first snapshot of the initial statistics that we looked at here is just looking at our window on either side of the eclipses, what happens to substorms, right? How often do they occur in those windows? And, is there some signature in this, in one of the auroral indices that we can pick out in the windows located centered around eclipses? And so we looked from year 2000 until December 2021, and we see that only 3 of those eclipses don't have a signature in the SME. That's the supermag equivalent electrojet index, and that's basically that previous index that I showed, but with a lot more stations. And so that's, I think, potentially an interesting feature, right? Of those 3 that don't have any significant signature in SME, those eclipses are occurring in regions where we don't really have the greatest ground mag coverage because there's not a lot of ground to put magnetometers on. So think like Pacific Ocean, right? You might have 1 magnetometer or 2 in Alaska and then nothing in the other hemisphere, right? Or it might be, in a region that's at a really high latitude, but you can't get, that kind of auroral region coverage. And so the other kind of interesting feature that came out of that is 70% of those eclipses have some kind of activity occurring within an hour of the eclipse window. And that's published substorms. And so there's a bunch of published techniques on how to identify substorms, and they're all fairly well accepted, with certain caveats. 70% of the eclipse windows that we looked at have substorms occurring within an hour. And, that's, I think, a pretty good and significant result in and of itself. Considering that automatic substorm detection isn't perfect, right? I'd say that's pretty decent performance for using eclipses as a selector for substorms. But we need to get better details on how significant is this correlation, if it's of interest to the community. And so our first kind of stab at that was just to do something similar to what we had done with the histogram plot that I showed previously, but a little bit more formal. We do a Gaussian kernel density estimate. Basically, you take those, when a substorm is occurring with relation to the eclipse time, how far it is from the central eclipse window time. You fit a Gaussian to each one of those bars, and then you get this distribution of multiple Gaussians, right? It's a sum of Gaussians. Typically, so because of the way that we structured this, we had one value where if you don't have a substorm occurring in the window, we report that as some error value outside the window, right? So you would get effectively a bimodal distribution where you'd have the sum of all the Gaussians that represents substorms occurring in the window, and then you'd have another Gaussian which represents substorms not occurring in windows. And so that gives you this bimodal distribution that you can then compare windows. And so I want to say, okay, yeah. So this plot right here is a little information dense, but we'll get through it together. So the green peak, this green distribution here, is substorms occurring within the specified window centered on the eclipse, right? So minutes from epoch. And most of them occur in the center of the window, which you would expect, convolving a boxcar with, some random sample of data. But we have this slight other peak here at 300, which is outside of our window, right? And so this peak represents how many substorms occur in the window, how many windows don't have substorms, right? The red line is that same interval, but then shifted by a day. And so we can see that this peak is much smaller, representing fewer windows that have substorms in them. And again, this peak is higher, representing more windows without substorms. And we can do this for a bunch of different offsets, right? So this is offset of a day, this is offset of a Carrington rotation, this is 2 days, and it's pretty close, the distribution here. But then again, you look at how many windows don't have substorms occurring, and that's much higher than the eclipse-centered window. And then this is one, a year later. And again, they all have the same kind of overall theme, where if you look at the windows around eclipses, substorms occur more often than just random windows that you pick, right? But this isn't really a good quantitative analysis. This is kind of, again, just getting that intuition, that feeling that there's something here, but we want some hard numbers to look at. And so we achieve that by using pointwise mutual information. And so if you're unfamiliar with how this technique works, you basically take the occurrence of, 2 events, right? I've just got the simplest kind of layout here, which is an onset occurs and an eclipse occurs, right? And it either happens or it doesn't, right? There's no in between for this kind of setup. And then you do, distributions for both of these types of events. How many, you break your entire time series up into a bunch of windows. You go and you look how many windows does this occur versus not occurring. And then you do the same thing for your other variable, and then you compare those with the probability of co-occurrence compared to the multiple of their occurrence. And that gives you a value that represents basically how likely they are to co-occur compared to random chance, right? So I think I have an animation that shows kind of the convolution of that window. And these are the actual values that you get taking that 21 years of data, X being substorms and Y being eclipses. And so you can see substorms occur, roughly 40% of the time for any given 2-hour window in that time period. And eclipses occur, 0.05% of the time, right? So they're much more rare. And yeah, I mean, the sum of these two should always be 1 for each individual variable. And it's when you do this cross multiplication that you get a score that relates the two. So yeah, like I said, in any given 2-hour window, there's nearly 40% chance of a substorm having occurred. When you look specifically at windows centered around eclipses, this rate jumps up to 67%, which again is I think a remarkable detail that comes out of this analysis. Is we can say definitively the likelihood of an eclipse having, or a substorm having occurred during an eclipse, shoots up by 27%, right? Then we go through a process of looking at the PMI scores for each of the possible scenarios, right? So this one is, no substorm and no eclipse happening. We get a very small value. We get a substorm happening, but no eclipse happening. We get another very small value. We look at substorms not happening during an eclipse, and we get a negative value. And then we look at eclipses or substorms happening during an eclipse, and we get a positive value. And the PMI scores themselves are a little bit awkward to interpret because they're not typically normalized to a well-known range of values. And even then, it's not exactly, depending on which method you use to linear or to normalize them, they're not exactly linear representations. So there's some play here in how you can interpret the actual magnitude of the PMI scores, but the sign is really what's important, and the kind of relative magnitude for the scores compared to say other scores, right? So 0.2 being a much higher value than this 109 times 10 to the negative 6 tells you that this is far more informative than this value here, right? But the negative values means that something is less likely to occur than random chance, and the positive values tell you that something is more likely to occur than random chance. And so when we go through what is probably the most applied normalization method for these scores, we see that still the probability or the score for substorms happening during an eclipse is positive, and the score for substorms not happening during an eclipse is negative, which again supports the conclusion that it is more likely than random chance to have a substorm during an eclipse, and it is less likely than random chance to have a eclipse without a substorm. And so this uses a 2-hour window, and we can change the window and get some different results for the actual PMI score, but the trend stays the same, right? So negative where it's negative here, and positive where it's positive here. And the values only change by about 15% if you change between 2 and 16 hours. And so one way of kind of validating the statistics is doing this comparison with a third variable, right? And so you might look at variables that are well correlated with one of the variables that you have in play, or you might look at variables that should have no correlation, right? And so I can present some detail on that. This is a CPMI study, a comparative pointwise mutual information study, looking at a third variable, which is days when the US AAA rated bond yield exceeded the 28-day median value, which should have nothing to do with eclipses or geomagnetic storms, outside of particularly wary stock traders. And yeah, this should be totally uncorrelated with anything. And so we can go through, do the math, crunch the numbers, and again, we get the same kind of results: negative whenever substorms don't happen during an eclipse, and positive whenever they do happen during an eclipse. And here's kind of the most important bit of information here. Pardon the pun, but the additional information that we get by adding this third variable is very small, especially in comparison to the original value, right? So this is the difference value, and you get practically no additional information by adding this, effectively random nonsense variable. Doing the same thing with a value that should be correlated pretty well with substorms, which is the polar cap index, basically the measure of the potential across the polar cap. It's basically in that circuit, it's the voltage across the ionosphere, right? And that should be well correlated with substorms because that's part of their phenomenology. And again, we get the same trend, right? Negative and positive, where negative and positive are expected. And again, the additional information gained by adding this variable is fairly small. It's 5% of the original value. And so we're not getting a whole lot extra by adding in something that's well correlated, which tells us that the correlation isn't subject to, random noise or random fluctuations, right? And so I'll bring up the conclusion slide here and just kind of touch on some of the ideas why this might be occurring. And so, yeah, back to our conclusion here. I'll beat the dead horse and reiterate that substorms occur more often when eclipses occur. The intuition that I have for why this might be happening is, again, related to how you're changing this R value, right? And so this is just a real simple model of, an inductor charging, right? This is an LR circuit charging up, and then at some time period, you vary the resistance down from a nominal 12 mho down to 7, and then back up to 12, right? And so you can imagine this is your eclipse period, right? Where the sun disappears fully here and then reappears and reemerges, right? So this shaded area is the current that would be going into the ionosphere, but is now going into the magnetosphere, right? If the potential, stays the same. And so if you're pumping a bunch of extra current into the magnetosphere or the magneto-tail, then, that seems to be a good reason for why a substorm might start. If you do this analysis for the eclipse that we studied in 2021 December, and I just submitted a paper on this, the magnitude of the energy that you end up diverting from the ionosphere is about the same as what previous studies have seen is necessary to trigger a substorm. So, it could be that that's really all it is you're just taking energy out of the ionosphere. You have energy that would typically go into the ionosphere. You're basically plugging a hole from a balloon, that had a slow leak and is still being filled. And eventually that balloon just pops, right? Because it can't leave out any of that pressure anymore. But that said, we don't really know the exact details of what causes this kind of correlation to occur, right? We can look at this in better detail by sensing, the currents that are coming in from the night side region, planning to have satellites in that region that can measure current or measure magnetic deflection and see both in space and on the ground what's happening to those current systems. That kind of thing is really necessary to give us a better idea of how these two phenomena are linked, if they are physically linked, which I tend to believe based on the evidence I've shown thus far. So that said, that's not the only thing that we can do. Campaigns are great, and putting instruments in more places keeps me employed. But there's other statistical tools that are at our disposal that we could use. Some real simple ones. The SME index is available from at least 1980. I think it goes back maybe another 10 years before that, with fewer and fewer stations. And eclipses and eclipse data exists, we can send it back, hundreds and thousands of years. So we can look at all of those events and, establish this this trend a little bit more robustly, if it, doesn't just wash out with more data, right? And we can also do a more detailed analysis using less, I'll say more finer resolution data, right? So imagine instead of doing just a on-off type of comparison, right? Where an eclipse happens or it doesn't, you create a value for, some scalar value for the obscuration, right? You have a global eclipse impact parameter or something like that, and you can measure this, impact parameter as it moves across the Earth and has a global impact on the ionospheric current. It's a range of values between 1 and 0, and then you can correlate that with the actual numerical value of the SME and get perhaps greater detail. Maybe that has to be done with the change in the SME or something to that effect. But in any case, there are a bunch of other features that we can look at to get perhaps more information on the correlation between these two variables. So I will leave it there and see if there are any questions, comments, concerns, criticisms, whatever you got.
Oh, excuse me. As soon as I was about to go, I got a bug in my throat. Well, thank you very much. Saying it's very interesting to see a very surprising result of the basic limitation there is that of the eclipses that you were able to find and study, the ones that don't, maybe there's not a substorm just because they weren't able to detect the substorm for it. So the one kind of thing I didn't know, if you looked at I think like a plus or minus like hour window around that for if the substorm is happening during the eclipse, is how, I guess, where do you have a sense of how tight of a time window you could take that before you really break things? Like if you went down to plus or minus like a half hour, does that drop out 10 of them or 15 of the events? Or
Right, yeah, that's a good question. So I've kind of done the opposite, right? I've gone out to 6 hours to see just how much variance I get there. But yeah, I haven't done anything like I guess that would be like a sensitivity study to see how narrow of a window I can still get meaningful information out of. Yeah, I think that would be an interesting aspect to look at, and perhaps useful in the sense of maybe doing. I could see that being a useful feature for some kind of prediction algorithm or something. Looking at when a substorm's going to occur during an eclipse, right? You have an eclipse period coming up. When those happen, and so you want to time when it's going to happen, when the substorm associated should happen.
Yeah, what's the probability kind of thing that's something's going to happen 30 minutes before versus 30 minutes after versus during a peak kind of thing.
Yeah,
cool.
Yeah, I also want to mention too, just because I have the graphic available somewhere at the end of this. Yeah, so the other aspect here too is all of these high latitude indices that we use are at high latitudes in the northern hemisphere, because that's where all the land is. And so we've shown in previous studies, as well as others have shown, that eclipses have a interhemispheric effect, right? And so again, to your point, it could be that those few just don't have the spatial coverage for sensing, right? It's could be a sensing issue and not an issue with phenomenology.
Yeah.
So
yeah. Any other questions? I guess other future looking thing is, right, we have two solar eclipses coming up across the United States, or at least North America, between October of next year and April of the following year. Is there any thoughts on I don't know if you're thinking of anything particular, but any I don't know, not predictions, but any kind of things you might be interested to see and maybe study out of those two?
well, I'm I'm definitely expecting there to be substorms that occur during them. I guess as far as like actual concrete plans, I am looking to potentially do a postdoc proposal focused on deploying some instrumentation for the 2024 eclipse. I don't think I'll be able to get things done in time for the one in 2023, but yeah, so one of the phenomenon that came out of the case study from last year's Antarctic eclipse was an association of a particular type of ULF waves that occur during the eclipse. And so there's a couple different explanations for how those waves are generated. Some of it requires thermospheric disturbances and you know, an upwelling of electrons. Some of it is a conductivity related, you know, asymmetry in the conductivity of the magnetic footprints. And so there's a couple aspects that we want to look at in greater detail. So deploying instruments, you know, ground magnetometers, of course, just because they're cheap and easy and useful, but you know, neutral wind measurements would be ideal. There's a lot of ideas that we've got, you know, kind of on the back burner for those eclipses for sure.
Okay, well, I think it's mostly just you, me, and a few students here, kind of thing. So we'll end it there. And thank you very much, Shane. This is certainly very interesting. And thank you for sharing it with us here today. But
yeah, thanks for having me.
Yeah. So otherwise, we'll end it there. And everybody have a good Thanksgiving break next week, and we'll come back the week after Thanksgiving with another kind of more long running Virginia Tech satellite project that's called InspireFly, and we'll be hearing from that team here in 2 weeks. So everybody otherwise have a good Thanksgiving break, and we'll see you in 2 weeks.